Okay, let's talk about thermochemical equations. Thermochemical equations is a balanced reaction plus the delta H value for the reaction, or we can just write the heat either as a reactant or a product like we've been doing. So we got our friend combustion of pentane liberating 3,523 kilojoules. Now, for that to be a valid heat for this reaction, the stoichiometric coefficients must be interpreted as moles. So we say 1 mole of pentane, 8 moles of oxygen reacting to form 5 moles of CO2 and 6 moles of H2O in the liquid phase. Equivalently, we could just as easily say that same reaction where the delta H is a negative 3,523 kilojoules. Remember, negative would mean it's exothermic, positive would mean it's endothermic. So let's talk about standard states, standard enthalpy changes. These standard conditions for gas, you shouldn't confuse those with gas laws or STP because they're not the same conditions. Temperature is 25 degrees Celsius or 298.15 Kelvin. Pressure is 1 atm. For pure substances like solids and liquids, that's just the standard state. For gases, the standard state is 1 atm of pressure. For gaseous mixtures, the partial pressure must be equal to 1 atm. And for aqueous solutions, the standard state is 1 molar concentration. Let's talk about Hess's law now. Hess's law of heat summation states that the enthalpy change for a reaction is the same whether it occurs by one step or by any perhaps hypothetical series of steps. That's true because delta H is a state function. And it'll work for any other state function, not just delta H. When we do the next chapter, there'll be a few more thermochemical quantities that are also state functions. All this will work for that. So here are the steps that has to be followed. If this occurs in a series of reactions, then we're going to need to rearrange those reactions if necessary so that the reactants and the products are on the same side of the equation as they're in the reaction that we're trying to determine. If you flip that reaction around, you have to reverse the sign of the delta H, that is, you flip from positive to negative or vice versa. If you multiply an equation to get the coefficients to be right, which you will have to do sometimes, then you must multiply the delta H for that same coefficient. So let's look at a starter problem here. And let's say we got methane plus oxygen producing CO2 and water, delta H 91.8 kilojoules. So in B, I have 4 CO2s, 2 waters, 2 methanes, 4 oxygens. What's the enthalpy of the reaction B? So what did we do to this reaction? We flipped it and multiplied all the coefficients through by 2. So in the end, the enthalpy is just going to be positive, and we're going to have to double that value, 183.6 kilojoules, because we had to flip it. We had to flip that first reaction, and we had to multiply it by 2 to get the answer. So this was just a starter problem so that we could see what the rules would be. So we flipped it, we multiplied it by 2 to get the answer. Now let's look at a more robust problem that goes through everything. So using Hess's law, we're going to determine delta H for reaction 3 using reactions 1 and 2. You have the delta H for both of those reactions, and we're going to use the knowledge we have to arrange those so that the first 2 reactions add up to be the third one. All right, let's look at this process. I've copied all of the things from the problem. Now, to get everything on the right side, we're going to have to get everything to match up with that third reaction. So I like to compare what's the same. So we got this FeO here compared to that FeO. And when I compare that, they're on the wrong side, so I'm going to have to flip this one. The coefficient's 2 there and 4 there, so it's also going to have to be multiplied by 2. Fe2O3 is on the product side, same coefficient, so I'm going to do nothing to that one. So let's make sure this adds up now. So we're going to take it and multiply it by 2 and flip it. So we're going to say 4FeO solid reacting to form 4Fe solid plus 2O2 gas. And then didn't do anything to the second one, so I'm just going to copy it. 4 Fe solid plus 3 O2 gas, forming 2 Fe2O3 solid. Let's look and see what cancels. Anything that has in the same state, same substance, is going to cancel across the reaction, so the ions are going to cancel. Now, there's more oxygen here than there, so those two will cancel, and I'll still have one left there. Now, does that add up? Actually, it does. You're going to say 4FeO solid plus O2 gas goes to form 2Fe2O3 solid. And so the reaction matches, so what about the delta H's? I recommend making sure the reactions add before you mess with the delta H's. That way you're not wasting effort. So the delta H for this first reaction is, you flipped it, so it's going to be a positive, and I'm going to multiply it by 2, so positive 1088 kilojoules. Didn't do anything to this one, so I'm just going to copy it over again. Negative 1648 kilojoules. And so the delta H for the final process is a negative 560 kilojoules. And that would be our answer to the question. This next reaction, you have 3 different reactions. You have the delta H's again, and you want to know the delta H for that last reaction. So we're going to flip, we're going to multiply, and then we'll make sure they add together to give the fourth reaction. We'll use it to get the delta H of the reaction we do not know. So let's look at this particular problem. I've given you the reactions from the text. So we have all the delta H's, all the reactions. Again, we're trying to find this fourth one. We need to decide what we're going to do. Okay, if I look at the NO compared N2O compared to the N2O, I'm going to have to flip that to get it on the correct side of the reaction, and the coefficients don't match. So I'm going to have to multiply that by 1/2 or divide by 2. Now the NO2 or the NO is compared to the NO down here, right side, so I don't need to flip it, but it's a 3 versus a 2. To get that to work out, you're going to have to go 3 halves. And you're going to end up with some fractions in this problem for coefficients, but they'll end up canceling by the end. So it's okay. Just let the fractional coefficients go in this case. Then we got NO2. NO2, the coefficients don't match, so we're going to have to flip that one and multiply by 1/2, just like we did for the first one. Now we're going to have to put down what we've got for each of these after we've manipulated them. So we're going to flip it, divide by 2 essentially. So N2O gas reacts to form N2 gas and 1/2 O2 gas. Second reaction, since we multiply by 3 halves, it's going to be 3 halves N2 gas plus 3/2 O2 gas going to form 3NO gas. Coefficient here is right, but I do end up with some fractions, and we're going to work on that. And here I'm going to flip and divide by 2 as well. So it's going to be NO2 gas reacting to form 1/2 N2 gas plus O2 gas. Now let's make sure they add up. If we look at the nitrogen, we got 3/2, but we got 1, which is 2/2, plus 1/2 is 3/2, and so all the nitrogens cancel. Then you're going to get the same essential thing for the oxygens, 3/2, 1 plus 1/2 is 3/2, so we're going to cancel all that out. And so we find, in fact, it does add together, N2O gas plus NO2 gas reacting to form 3NO gas. Now let's manipulate the delta H's now that we know that we're working with the right thing. So if we flip this first reaction, divide by 2, we get a negative 82.1 kilojoules. Delta H for the second one, if we just multiply by 3/2, we get positive 270.8 kilojoules. Delta H for the last one, again flipping and dividing by 2, negative 33.2 kilojoules. Adding all that together, we're going to figure out the enthalpy for that final reaction is a positive 155.5 kilojoules. So that's an endothermic reaction.